Hello mathematicians, let's dive into another proof by induction. So this time we're going to be proving that the sum of a bunch of powers of 2, or excuse me, 1 over a power of 2 is going to equal 2 to the n minus 1 all over 2 to the n. And because I know we always want to see some extra practice with sigma notation, we can see it reverted out here as well so we can get some practice. And I always like to show where this right-hand side formula comes from. And it's actually not that bad to see the pattern sort of show up. So if we start off with just one term, 1 over 2 to the power of 1, well, that's just 1/2, which can be rewritten as 2 minus 1 over 2. That's not so bad. Let's see it for this one. We got 1/2 plus 1/4. That's 3/4, or 4 minus 1 over 4. We can see this again for up to 8. So we got 1 over 2 plus 1 over 4 plus 1 over 8. That's 7/8, or 8 minus 1 over 8. So it's really easy to see this pattern sort of pop up. So that's where this right-hand side of our equation comes from. Now, let's dive into the actual proof. Now, I like for proofs by induction to be a 4-step process. Now, officially, it's just a 2-step process. We solve for a base case, and then we show the induction step. I like to think of it as a 4-step process. And the first step I always like to start off with is to state our goal. What are we trying to show? We're trying to prove the conjecture on the previous page. And how are we going to do that? We are going to show have to pardon me not being able to write. We're going to show that P of K implies P of K plus 1. And so what's that mean? What does that mean? That means we're going to eventually have an equation. We hope to have an equation we're trying to aim for an equation that looks a certain way. Well, what way might that be? Well, if I look over at my original problem, we've got 2 to the n minus 1 over 2 to the n. Well, let's just substitute a k plus 1 everywhere we see an n. So that's going to be 2 to the k plus 1 minus 1 over 2 to the k plus 1. So that's our goal. That's the target we're trying to hit. That's what we want to eventually find. But how do we do that? We move on to step 2. Step 2 is where we prove a base case. Right? Prove a base case. That's just show me somewhere where this works. And typically, if you can get away with an n of 1 or an n of 0, that's great. That makes the math shake out really easy. We've already done that. Right? Over here on the previous page, I worked these base cases for n. I started 1, works for 2, works for 3, happens to work for 4 as well. You just end up with 15 over 16. So this works for a couple. So I'm just going to give it a little check mark. Why? Because we've already done that. We did it on the last page. Which kicks us over into our step 3. Now our step 3 is a little bit different from like the official step 3. Remember, the official instructions for a proof by induction says to prove a base case and then do the induction step. I like to break these down a little bit more, so I'm just going to very explicitly say that we are going to assume P of K. Well, what does that mean? We're saying that P of K will be 1 over 1/2 plus 1 over 4 plus 1 over 8 plus all that other stuff plus 1 over 2 to the k is equal to the k minus 1 divided by 2 to the k. Going back again to that original problem, right, we've said, I've just plugged in a value of k everywhere I saw an n. We're just making an assumption. Excuse me, we are making an assumption that this is true. Which leads us in to step 4. This is the second half of our induction step. We're going to show that P of k implies P of k plus 1. So if this part is true, if this statement is true, then this statement is also true. So we're just trying to say, does this work somewhere? Is there some number where this works? Well, yes, there is. We worked a couple of them. You can see them on this page. So we don't really know about that at this point, right? We just say, does it work somewhere? And what we're trying to show, is there some later point where this also works? Now, we're working with integers here, and it is great that we can always just say plus 1, and that'll grab us all of the integers. So it works out really well for these sorts of problems. But what would that look like? So we have p to the k plus 1 would be 1 over 2 plus 1 over 4 plus 1 over 8 plus all that other stuff plus, and that would be 1 over 2 to the k plus 1 over 2 to the k plus 1. So I'm just showing the previous term, right? This is our target. This 2 to the k plus 1. This is just the one that came before that. And all of that being equal to 2 to the k plus 1 minus 1 over 2 to the k plus 1. So this is our right-hand side down here, and this over here is our left-hand side. Now, at this point, we can say, I know what our goal is. Look at this part right through here. That should look a mighty bit familiar. It should look familiar because that is this part up here. And we know the value for that. It's this. So let's actually just sort of write that down. This is 2 to the k minus 1 all over 2 to the k. We're allowed to say that because we made that assumption. We've said that this part is equal to that. There's some point where this holds true, and that's what we're showing here. So we're using that to our advantage. But we're not done yet, because we've still got this part to worry about, right? We've added this plus 1 over 2 to the k plus 1. Now, where do we go from here? It's not immediately obvious. But if we were to take this equation and rewrite it just a little bit, let's remember how exponents work. Right? If we have, say for the example, and let's maybe do this in a different color. I like using different colors. I think the math works out easier. If we had 2 to the 4, well, that is 2 times 2 times 2 times 2. But what if we just took this part right here, and that's 2 to the 3 times 2. So we can take 1 away and bring it out front, and that is our key for this next step. So I'm just going to spend a little bit of time rewriting the equation we stopped on. That was 2 to the k minus 1 all over 2 to the k plus 1 over 2 to the k plus 1. So let's use that property of exponents that we just showed to show this. We got, 2 to the k minus 1 all over 2 to the k plus 1 over 2 times 2 to the k. See what we did there? I just pulled out that exponent to show that extra 2 out in front. And now it's really clear that these have almost the exact same denominator. All we're missing over here on this side is a 2. At this point, we should know how to multiply by 1. Multiplying by 1 doesn't change anything. Hopefully we can see that 2 over 2 is equal to 1 because any number divided by itself is equal to 1. So if we multiply by this funny looking version of 1, we get 2 times 2 to the k minus 1 all over 2 times 2 to the k plus 1 over 2 times 2 to the k. So all I've done is I've just multiplied this one out. Now we've got a common denominator, and if I work through the algebra on that, well, that's going to be 2 times 2 to the k. Well, that's just another exponent, right? We can just say that's 2 to the k plus 1, and 2 times negative 1 is negative 2. And here, we've got the same problem. This is 2 times 2 to the k. Well, that's just 2 to the k plus 1. I'm going to go ahead and extend this out. And we've got the common denominator at this point. We can just say plus 1 for the whole thing. We're almost done. There's just a little bit left to simplify. We've got 2 to the k plus 1. We've got a negative 2 and a positive 1. Well, that works out to be just a negative 1, or subtracting a 1, divided by 2 to the k plus 1. Now, at this point, let's go back and look at our original goal. Remember, we had a goal for all of this. We were trying to prove some conjecture, and we said that we'd eventually have an equation that looked like this. 2 to the k plus 1 minus 1 all over 2 to the k plus 1. Wouldn't you know, that's exactly what we have here. 2 to the k plus 1 minus 1 all over 2 to the k plus 1. This is what we had to show. Therefore, the induction shows that P implies, the induction would show that P to the k implies P to the k plus 1, proving our induction step, and thus proving the conjecture. Thank you for watching.